Thank you very much, Adam, for the introduction. And first of all, I would like to thank you, the organizer, for inviting me here. I mean, this is a fantastic conference. I'm really having a blast interacting with the young faculty members here. And well, I'm really looking forward to the next editions of the conference. So I would like you to remember this presentation as the odd one. This is going to be the weird one. But the title of the presentation is Acceleration of Chemical Reactions by Mechanical Distortion. And Adam already allured to the fact that I'm going to talk about something called mechanochemistry. So first of all, I'm terrible at creating introductory slides. So while procrastinating on this, I decided to cheat a little bit. And I asked an image generator to give me an example of what is a chemical reaction. And this is what it came up with. And this is actually a fairly good answer. So we see a color change here. That's what we commonly associate with chemical reaction. But there are also two other features on this picture. The reaction takes place in the solvent, and there are vapors here, meaning there is some source of energy. So effectively, what we're looking at here, it's a solvothermal reaction, which involves heating reactants in a solvent bath to activate chemical transformation. And if we scale this reaction up, this is effectively what chemical industry is doing. And as the result of this, because we need all these solvents and energy to heat up solvents, the energy industry, the usage of organic solvents in chemical industry accounts for more than 60% of all chemical manufacturing waste, as well as 37% chemical industry consumes 37% of the total energy used in manufacturing. And these simple facts are very difficult to reconcile with the principles of green chemistry, which will ask for using a benign solvent, be energy efficient, or improving atom economy. So let's ask a simple question: why do we need this thermal energy and solvent in the chemical manufacturing? So this is a potential energy surface representing a simple chemical reaction where we go from the substrate A to the product B. And of course, along the way, we have to cross the transition state and pay associated activation energy penalty with that. So in the case of the solvothermal activation, it means that we are providing energy to overcome this reaction barrier to form or break a bond. And we know from the physical chemistry classes that this reaction rate is described by the Arrhenius equation, which is just a Boltzmann population factor of a transition state times some empirical factor Arrhenius constant. Or more formally, this is described by the Eyring-Poliani formalism, where there is this parameter here called the transmission coefficient. But what's also important to notice here is that when we are providing the energy to the system, this does not only activate the one single reaction coordinate, but the energy dissipates among all possible coordinates in the system. So our idea is to introduce a directed force. So in mechanochemical activation, this means making and breaking of this chemical bond as a result of applied force, which will act along this reaction coordinate. So effectively, this has been described by the Bell theory. You see that here the Boltzmann population factor, the energy of activation here, is reduced by the magnitude of the force times the displacement delta x. So as a result of this, because we are decreasing the activation energy, this will generate increased yields of the reaction, but also increase the rates and the higher yields, but also can result in the reduced waste. Or if we have a competing reaction processes, it can generate alternative selectivities of the reaction. And of course, this idea is not new. People have been using mechanochemistry over the millennia. And it works in practice. I mean, there are different types of mechanochemical instruments. We can talk about the ball mill reactors in a small laboratory scale, or a twin screw extruders, which will generate products on the kilogram scales over in the continuous fashion. And there are two major theories that explains why mechanochemistry works. The first one is the hotspot theory, which says that the colliding particles in such a ball mill reactor causes localized spots of intense heating that will drive the reaction thermally. Or there is another theory, surface area theory, that will tell that the milling increases the surface area and mixing of the reagent, and thereby increasing the reaction rates. However, there are two problems with these two theories. The first one is that nobody ever was able to observe this increased temperature of the reactants, and in situ Raman measurements show that they're only increased to up to 10 degrees Celsius, whereas the surface area theory explains why reaction would accelerate. However, it cannot account for a different alternative selectivities that would, because the reaction should still follow classical thermal trajectories. And there is an increasing body of evidence that indeed under mechanochemical conditions, this will yield different products. So for instance, here in the Suzuki coupling, under thermal conditions, we'll get a 1-to-1 product. Under mechanochemical conditions, which are commonly abbreviated as these 3 balls, it will yield a 2-to-1 adduct. And here's another interesting example where fluorination, which involves production of the HF as a fluorinating agent, which is extremely toxic, under solvothermal conditions, it yields these 2 products with a majority of the singly fluorinated one. Under mechanochemical conditions, we can actually circumvent formation of HF as a fluorinating agent and then go also to the doubly fluorinated product. So how to account for the fact that there is a force acting during the reaction? So we have to move from the potential energy surface to so-called the force-modified potential energy surface. And in the simplest approach, we can imagine that we'll observe the decrease of the activation energy that will manifest in the changed reaction rates. So if we will be able to understand this kinetics, how this force changes the potential energy surface of the reaction, this would lead to the better and more predictable mechanochemical reactions. However, the challenge here is that under mechanochemical conditions, we have more competing processes. We sorted them into 2 types of the reactions, so-called the primary reactions, which is responsible for the formation or breaking of the chemical bonds. But at the same time, we have all secondary reactions, such as grinding and mixing of powders happening in the reactor. And because these 2 processes are entangled with each other, there exists a substantial experimental limitations on how to measure the effect of the force on such a simple parameter as a reaction rate. So this is the goal of this work, that we wanted to establish or wanted to derive these basic parameters, and we chose a simple pericyclic reaction, Diels-Alder reaction, addition of a diene and a dienophile, 4+2 fashion, going to the Diels-Alder adduct. So this is a very simple reaction that has only 1 transition state, and it has been well studied by organic chemists. What is also known is that this reaction is sensitive to the applied pressure. The reaction rate will increase with the applied pressure, and then the slope of this derivative is equal to the volume of activation, which is a difference between the volume of the individual molecules and the volume of the transition state. And has been experimentally derived that this is usual volume of activation of these in the Diels-Alder reaction. And it has been also so well studied that we know how to modify these reactants in order to accelerate this reaction. And we can take a look at some of the literature. So for instance, here we see that indeed this works. If we have an electron donating diene, then this leads to the lowering of the transition state. Here we have a increasing of the activation energy. But also, this reaction changes when we apply mechanochemical conditions. So we see that upon grinding, there will be a different conversion rates, and then there will be a different selectivities if we change between mechanochemical and solvothermal. So this is all great, but there is still a fundamental problem, being that the most basic kinetic parameters, such as force, temperature, and concentration of this reagent cannot be measured. And the explanation that I'm showing you here are purely phenomenological. So that was the goal of our work, where as the 4 PIs, we look at in details at the Diels-Alder reaction and see how the reaction rates will change upon applied force. And the general idea was that we'll have a diene immobilized on the surface chemically, and then there will be a external force with a dienophile embedded on the ink acting on this diene. And then if we are able to measure what's this force and how long we are applying this force, we should be able to derive the kinetic rates of this reaction. So for the experimental setup, we use a massively parallel polymer pen lithography. So the idea here is that it works like a nano printer where we're using this this polymer printer with ink and covered with ink that can be used to print features on the surface. So our experimental approach was to start by immobilizing anthracene chemically on the silica surface and then acting with a diene that's embedded in the ink in the polymer print as acting with the force in order to generate this Diels-Alder product. And we synthesize 4 different dienophiles. So the dienophile is just this fragment over here. The rest is the fluorescent probe that we use for reading the reaction outcome. So there are several advantages to run this experiment like that. First of them being that the monolayers would remove a particle-particle effects. Effectively, we're just looking at the monolayer of anthracene. And also, we have a precise control over time and force at each of the reaction spots. Furthermore, there's a high throughput system because we are able to use this in the parallel fashion. So we'll get some statistics on the experiments. And effectively, we can determine reaction rates as a function of this time and force because we have a very precise control over it. And what turned out to be also a significant advantage is that the reaction is happening under uniaxial stress, meaning that the force is acting among a very specific reaction coordinate. So of course, there is a lot of proof that that we measure exactly what we wanted to measure. So first, we check that there is indeed immobilized with a time of flight, secondary ion mass spec, and XPS, that indeed we are able to immobilize anthracene on the surface, and then also that we are able to detect the Diels-Alder product after the reaction. So once again, how an experimental setup looks like. So this polymer lithography, so the machine here itself is tilted, so by such we are able to differentiate between different forces acting at the different spots. And so this is how the experimental output will look like. On one hand, we have an increasing force acting on these reaction spots, and on the other hand, we are increasing the time of the reaction. So we have multiple measurements for each force and each time of the reaction. So also we make sure that indeed we are getting just the Diels-Alder adduct here. So if we, for instance, remove the alkene, the diene, or we remove the anthracene from the surface, so after washing, there is no signal. Fluorescent signal is only when we have a Diels-Alder reaction happening. So how to read what we have here? So what we need for that, we need maximum intensity, fluorescence intensity, as well as the surface density of the adduct. And then just by the difference between maximum intensity and the measured intensity, we'll get the density of the adduct on the specific point of the surface. And to do that, we can use a quartz crystal microbalance, which is just a super precise scale that will tell us what, and we know because of that the surface density of the anthracene is roughly 1 molecule per nanometer squared, and the maximum density of the adduct is 85% of this surface density. So with that, we are able to start from these fluorescent images and convert this into an intensity as a function of a time and force, and from there go to the intensity as a product density as a function of time and force. So just to give a more detailed picture, what we have here is that, so in the case of the alkene acting as a dienophile, we see that there is an increase in the reading, intensity reading as a function of time and as a function of force. 3D plots are terrible, so we can plot it as like that. So you see that indeed this is a pseudo first order process. With increasing force, we have a faster formation of the product. And we are able to measure it for different dienophiles, and we see that there is indeed a different response of the system. So furthermore, we know this is a force, but we would like to represent our data in terms of pressure. So from group of Rob Karpik, they did a finite element modeling of the deformation of this piezoelectric here, and also calculated experimentally what's the pressure, which is simply a force over surface. And we know that this pressure will increase and level off around 0.3 megapascals. And there is a good agreement between the experimental and the measurement and what has been calculated from simulations. So we know what these pressures are. So with that, we can now restructure our first order plots as logarithm of the density of the anthracene, which is basically decay of the reagent in this system, and we see that with increasing pressure, there is an acceleration of the reaction happening. So basically, the slope of the line describes the reaction rate, and we can calculate these numbers, and we see that going from the 0.16 megapascal to 0.3 megapascal, for instance, for alkene, we have a 4 times acceleration, and for the methyl acrylate, we have over 40 times acceleration. Okay, but so now what can we do with these numbers? So we know that this reaction rate, so logarithm k, is a function of pressure. But then the parameter in front of the pressure, this is the volume of activation, what I define as this difference between the volume of the transition states minus volume of the individual reagents. So if we plot k as a function of pressure, the slope of these lines would be delta v. And we see that, okay, and these are the lines that we are getting. We see that indeed different dianophiles will have a different volume of activations. But really, what's interesting about is that when we compare with the actual volume of activations that we derive from here. So experimentally, I mentioned that there's around minus 40 cubic centimeters per mole. But then if we look at the volume activation in our experiments, we get numbers that are 1,000 times greater under this uniaxial press than what will be usually done under hydrostatic pressure. Which brings us to a very simple question. Why? Because if we think about volume of activation being that large, this is actually larger than just entire system. It doesn't make a physical sense. So there must be something else happening here. So on one hand, we did reactive MD simulations. I mean, that's a group of Ashley Martini did the reactive force field simulations of the immobilizing the anthracene on the surface and the deformation of this molecule upon applied pressure. And on our side, we modeled this reaction using a density functional theory. So this work has been done by my graduate student, Ryan Kwok. And this is the image that we are starting from. So we know that there is a change to the energy of activation as the applied pressure. So we started by simple modeling of this reaction, where we calculated the energy of activations of 82.8 kilojoules per mole. So we look at all four the dianophiles reacting here and derive all these transition states. But now, question, what we are actually looking for? So we are looking at this effect of the force-modified potential energy surface when we are expecting decrease of the energy of the transition state upon the formation of the system. And this is one of the early images that we had in this work, and I think this is a very compelling image that tries to explain what is happening here. So we see that there is a bending of anthracene, and then there is this reaction of the dianophile being pushed into the anthracene. I mean, that's a pretty logical picture, right? So we try to scan the transition state energy as a function of this bending angle. So here in the silica carbon-carbon or the oxygen silica carbon. And what we observe is that the transition state energy does not want to decrease. This is an opposite effect. We always increase the transition state. So this took us a little bit of time in order to understand maybe what are the different coordinates that we should sample. And we came up with this coordinate that bending of the carbon-carbon-hydrogen angle and only towards the reagent, towards the diene, which sits on this side, will lower the transition state energy of this reaction. So just to highlight what we have here is that this is a relaxed transition state. And what we want to do is to bend this hydrogen towards the dienophile. So this leads to the formation of so-called the distorted asynchronous transition state. It's been described in the literature. And this bending of this hydrogen, you see that there is a small change in the bond length, which releases a little bit of the Pauli repulsion energy. But I mean, at this point, you could argue that transition state, by definition, critical point on the potential energy surface has the lowest energy. So there must be something else going on. So what's important to notice here is that indeed we increase the energy of activation, we deform the transition state, but at the same time, the deformation of the reagent is larger than the deformation of the transition state. So effectively, the energy of a transition state decreases. And we can represent it like this on the little bit more simplified potential energy surface when there's a first step leading to the deformation of the reagent that's happening under rather mild pressures. And although the energy of the transition state increases, the overall energy, activation energy of the reaction will decrease because it costs more energy to deform the reagent than the transition state. And this is different from the reactions under hydrostatic pressure, so thermal reactions, which as I showed has this volumes of activations -40 only, because in this case, this term P delta V, it decreases the activation energy, but because the V delta V is so small, this requires a substantial pressures. So in our case, we can achieve the same effect under rather mild pressures, but you see that this is a different mechanism than just a simple hydrostatic pressure which pushes molecules into each other. And we can look like what has been done about similar work in the past. So there's in 2000s, there was a lot of work done on the so-called mechanoforce, where you use a force to break a chemical bond, to break the chemical bond. And we can compare the reaction mechanisms that we have here with breaking of this chemical bond. So in this case, when we analyze these papers carefully, we concluded that this is a somehow similar mechanism that first also leads to the deformation of the substrate, which lowers the transition state energy. But the difference is that here we are bond breaking. So effectively, we are approaching this problem from the opposite direction. In our case, it's a bond formation, so we are sampling the potential energy surface from the opposite direction. And since we published our work, there's been some response in the literature. For instance, this 1,3 arrangement in the such a strain molecule can be explained only if we include the stretching due to this part of the molecule, as well as it is possible to explain phenomenologically that the acceleration of the Diels-Alder reaction is due to the fact that we are indeed moving along the orthogonal reaction coordinate, so to some other parts of the PES, which has a lower transition state energy. And let me just, for the sake of time, I will actually skip this part of the talk and maybe just let me go straight to the conclusion. So what we showed here is that under mechanochemical conditions, this thermally slow reaction can accelerate as a result of the uniaxial stress, which is indeed forced by this force-induced distortion of the reagent that lowers the relative transition state energy. And by doing so, we have a feeling that this occurrence of the mechanical force accelerating the reaction is most likely wider than previously anticipated. And with that, I also like to acknowledge that this work has been done as a part of the NSF Center for the Chemical Innovation in Mechanochemistry, which was funded last year by the NSF and its association of the several colleges. And in principle, our goal is to address the grand challenge of scaling up the atomistic theories to enable the predictive macroscale synthesis. And with that, thank you very much for your attention, and thank you very much for the conference.
Thank you, Mateusz, for this talk, and that is open right now for the discussion. I look for the questions. The first one there, and then Darek. So on the left. So let's start.
So very nice talk. So I wonder if you could maybe give us a comparison. Do you think that this kind of studies can lead to better AFMs or scanning tunneling microscopes, sprinkling something on a substance, or or is it just very far away from it in terms of numbers? It's a very naive and probably stupid question.
Well, the question is absolutely not that stupid. All these experiments have been done with AFM effectively. So here, in order to have this control over force, what you do is actually you pull your polymer using tip of the IFM. So yes, So AFM has been used to study these reactions for a long time. Like what we are showing here is the first application of something different than AFM. In this case, polymer pen lithography.
But can it be used to improve resolution, like in some sort of like crazy super resolution type thing, maybe, or some type of weird application?
Maybe some kind of weird application indeed. Yes. Well, I think that, I mean, in this case, what we are really aiming is for, well, I would say that, you can maybe increase the chemical synthesis by taking AFM to, act with a force along a very specific coordinate in the system. But this would be doing chemistry one molecule at a time. This is rather slow process after all. And our goal is to rather scale up the entire idea of mechanical chemistry by understanding what's the effect of this force on the system first. But yeah, I mean, I imagine that also has a possible direction.
Okay, thank you.
And Darek, a short question.
So, okay, I will try. So thank you for the nice talk. So I have like a question related to the transition states, synchronous and asynchronous mechanisms. So as far as I understood, in your calculations, the synchronous is the one that is lower in energy.
Yeah, this is the fully relaxed transition state, what would correspond to your critical point on the PES.
Okay, but
Now,
I'm just curious because recently I went through some calculations of Diels-Alder, and it seems like I found also some papers that actually the asynchronous in many cases is the one that is lower in energy. So you go like through stepwise reaction instead of concerted. And also people, I think last year they found some like parameters basically defining these two bonds for both of them, like asynchronous parameters, which correlates quite well with the relative energy. So can you comment?
I mean, there are so many flavors of the Diels-Alder reaction, and I agree that there are cases where there is a large difference between these two bonds, and in this case, you will go for fully asynchronous transition state. We'll probably be able to derive these critical points along the reaction coordinate. However, indeed, here it's not the case. We looked through all possibilities, and that was the only transition state we're able to find. And then just to so here, does not correspond to something that will be classically considered a transition state because we pushed it out of this critical point. But this would correspond to the transition state on the force modified potential energy surface if we would to include a force as an additional parameter to the definition of the PES.
And this is DFT also MP2 or the geometries?
This is all M06XX. There is a great body of literature doing Diels-Alder with this Truller's functional, so we just chose something that's well understood to work in these systems.
Thank you.
Yeah, thank you. So we don't have much time, so if you would like to speak with Mateusz, then approach him during the coffee break. And Mateusz, thank you very much for your talk.